the co-organizer of the seminar, who will talk about progress report on experimental math project. Before I let Eddie start, an announcement. There will be a dinner celebrating in honor of the speaker last week, David Wilson, who defended successfully his master's thesis, and Eddie, who will give a great talk today, and also everybody in the seminar to celebrate the end of a very good semester, and out of respect for David, who doesn't like the usual food, we're going to go to a Japanese restaurant called Ido on 68 Eastern Avenue. And everybody is welcome to join us, but please let me know immediately after the talk. The dinner will take place at 6:45 p.m. right after the talk, 45 minutes. No, 55 minutes after the talk. Ido, 68 Eastern. Let me know if you can come.
Thank you, Dr. Z. So thank you all for coming, and thank you, Dr. Z, for inviting me to speak at the experimental seminar. So what I'm going to talk about today is joint work with Chetan Tonde in the audience. He's a fellow graduate student from the computer science department. And before I get into the meat of the subject, let me say something, a few words about the experimental setup, the experimental infrastructure. So for most of the project, I use Sage. So Sage is an open source, freely available alternative to Mathematica and Maple. And I believe that mathematics is a community effort, and that everything underlying the algorithms and the construction should be open. And Sage tried to implement this idea. So I encourage everybody who wants to try using some software for experimental mathematics to use Sage and to contribute to it. All right, so that being said, what I'm going to talk about today is a project which occurred in Dr. Z's class. So as a good student of the I don't know if I was good. As a student of the New Jersey School.
You're not good, you're excellent.
As a student of the New Jersey School of Experimental Mathematics, I took Dr. Z's class. And that year, the topic was number theory. And the project would not have gone as far as it did if it wasn't for Dr. Z's encouraging words and guidance and mentorship. So thank you, Dr. Z, for your help. All right, so most of number theory have been explored for a very long time, and it seems highly unlikely for graduate students to uncover new elementary fact about numbers. So what I'm going to talk to you about, hopefully, is a delightful exception to that rule, but if it's hardly new, then it was a whole lot of fun to rediscover the whole thing. So what we're going to be doing today is looking at integers through the lens of combinatorics. So when I say combinatorics, I don't mean combinatorics in the sense of counting sets, measuring sets, non-trivially defined, but I mean the combinatorics of using vertices and edges. Okay, and what we're going to be using today are rooted trees. So for those who never thought about a tree, well, you can build the analogy with these plants that we see. There's a root. I will refer RT, and there are vertices, other vertices that you can think of either branches or leaves. So the terminal ones are considered leaves. These we call them vertices, and notions that we're going to refer to over and over is the notion of children. So vertices that are hooked up to another vertex will be considered child. So these two are children of this vertex, and this one is a parent for these guys. We'll consider family of, so this is a root. So if I give you a set of such trees, we'll think of them as a forest. You can have many trees. They're all rooted, so you're dealing with a forest. But there are going to be constraints on these trees. So we're going to have a label set. For convenience, I'll choose the labels to be prime numbers. Okay, so think 2, 3, and 5. And what we're going to be doing is labeling the vertices of these trees using prime numbers. So primes are these integers that cannot be divided by any other integers by themselves. So let's do a labeling here. 2, 3, 5 is a labeling. 2, 2, 3 is a labeling. Now some labelings are not going to be good for us. And it's helpful to think of these labels as names that parents want to assign to their kids. So it will be horribly confusing to call 2 of your kids Roberts. Call 2 of your kids Robert. When time comes to eat, when you say, Robert, come and take your meal, it might be confusing to who's Robert you're referring to. So we would never want siblings to have the same label. Always, we would want a tree to be good if the siblings have different labels. So the name Robert can be passed on to the next generation. There's no problem with the parent calling his son Robert, but you would never want 2 brothers to be called Robert. So every time in our tree, 2 vertices have the same vertex, have the same parents, the labels should be different. These are the validly labeled trees. So this should not occur. 2 should not occur. 2, 5 can occur, and the parents can have as many children as they want. All right? So typically the label set would be prime numbers, the names are primes, and they will be finite. And the first part of the talk is going to be dealing with answering the following algorithmic question. So part 1. Part 1. Compute the forest of trees, so the trees are always rooted, of trees validly labeled, The label set has size n, so I'm using only n primes, the n smallest primes, and furthermore, I want the heights to be bounded, otherwise there will be infinitely many of them. I want the height of the trees in the forest to be bounded by an integer h which is greater than 2. Okay, so this is the algorithmic problem we're going to solve, and then in the second part of the talk, we're going to argue that this actually helps understanding properties of numbers, more specifically, understanding sifting primes can be applied to sifting primes. Okay, all right. So let's start with the meat of the subject. And to do this, we're going to do some algebra. So I'm going to define a natural, I believe natural, algebra over trees. Okay? So the first operation, building on the intuition of plants, is the grafting operator. So we're going to be first grafting trees. And the operator is the following. So to graft 2 trees, let me take an example. So I have a root here. I have 2, 3. Then I have, let's put here 7, that I want to graft onto 3 root 7. Okay, so these are valid trees. I'm not worried about that. Let me just choose here 5 for convenience. Okay. So grafting 2 trees essentially amounts to hooking up, merging the roots of these trees. So I merge the root of this one onto the root of this one to produce a new tree, which looks like what they do to apple trees. So this is 2, 5, and 3, 7. So it's not completely arbitrary. We'll see why one would want to do this later in the talk. 7. So this is the result of grafting the 2 trees. Is the operation clear? So grafting trees amounts to just hooking up the roots together.
You can't always do that, right?
So if we want the tree, the resulting tree to be valid, you have to be careful about the trees that we're grafting. But grafting can be done irrespective of whether the trees were validly labeled or not. So grafting is going to be valid in a condition that I'll specify later. So this is the first operation we're going to do. And I'm going to naturally generalize this to grafting forests. If we can graft trees, why not graft forests? So here's how we're going to think about grafting forests. So let F1 be a forest. It has the tree T1. It has the tree T2 all the way up to the tree TU. All right? And I want to graph this, so this is F1 equals. I want to graph this onto the forest F2, which has tree S1, S2, all the way up to SV. Everybody can see here? So the grafting of two forests amounts to grafting every pairs of trees in a similar way that you do the Cartesian product. So every entry here, every tree here is going to be grafted to each one of the trees in here. And that's going to give us here a set that has U times V. The number of trees in the forest is going to be U times V. So the numbers of trees here grafted to the trees here. So that's the first operation that we're going to be doing on trees over and over. And we'll build on the intuition later, why would you want to do this? The second operation, which is not so much borrowed from planting or apple trees, is raising trees. Raising trees for. So this is the most unnatural operation, but I'll argue this is actually important. So raising trees slash forest. So the raiser operator does something quite interesting. It does the following. So you give it a tree. Let's take here 3 that's rooted. And you give it another tree. Let's take here 2, 3. Let's put here 5. This tree is valid. The siblings always have different labels. So what this actually does is to take this tree and make it a parasite of this one by hooking it up to the leaf of this tree. And if there were many leaves, you would hook it up to all the leaves. So the result would be 3, then this would be hooked up to 2, 3, and 5. And this is rooted. Right, so you have this parasite tree that hooked up to the leaf, and this is a tree that is higher than the trees you started at. So we sort of think of this as raising the level of the tree. Okay, so this is what the raiser operator does. Now, we need a raiser operator for forest. It's going to be much more simple than...
What if you have more? You do it for on every leaf?
Yes, if here I have more than one leaf,
Yeah.
I'll do it for every leaf.
It's the same.
So it's the same tree.
The same tree gets
hooked up to every
hooked up
leaf.
to every leaf.
Yes.
In this case, only one.
Only one. And for the remainder of the talk, when the raiser operator is going to be used, it's going to be a tree on one leaf. So we're not going to need roots. And what if I gave you a forest here? What if I gave you, this is root, T1 all the way up to root T2. What if I gave you this? Well, what the raiser would do is create a forest that has exactly the same size, but the difference is going to be that all these trees are going to be raised by this guy. So you're going to get 3, and T1 is hooked up to a tree which is rooted. 3, so this is T1. T2 is going to hook up, this is still rooted, all the way up to, so this is 3, rooted, and this is TU. So this is TU. So you can raise a whole forest by a single tree, and that's all we need. We will never need to raise a forest by another forest. So a tree can be raised, you can raise a forest by a tree, but we will never need to raise a forest by a forest. Okay, now these are funny notations, but the claim is, once you have these two things, we can solve our problem. We can define a recurrence that is going to produce all the trees of bounded height using only n labels. So here's the algorithm. So if you want to construct the trees that have different labels but the height is only 1. The claim is this is easy to do. Here's why. Root. Then let's put here 2. This thing is going to be grafted onto root. This is 3. So this is grafted onto the last one, which is going to be the n prime. Root and pn for the n prime. So one thing that I should mention right away, the consequence of the grafting operation is that if you graft a tree to only a root, you get the same tree. Nothing changes. So you can think of the root as the neutral element of the grafting operation. All right? And furthermore, what I claim here is that when you look at the resulting forest, so you grab these two forests, then you graft until you get these, essentially you're going to produce all trees that have height 1, and this is essentially looking at subsets, the set of subsets of elements. So G1 was the easy part. It's going to give you all the trees you want that have height 1. And this is actually key to understanding the proof of the correctness of the algorithm when I specify it. And at the end, I'm going to have this tree with all the n. So 2, 3, and so on, the n. And so let me just write it together. Okay, so, and this set is going to have size 2 to the n. Because a tree, a given tree is missing this branch or is not missing that branch. Okay? So really, the question is, once you have this, how do you go about? How do you produce higher trees? To produce higher trees, you use the following recurrence. So Gm, the recurrence is defined by Gm plus 1. So these are trees. The forest of trees of height m plus 1 is equal to the grafting over all the labels. So I'm grafting over all the labels. This means all the n primes of the following, which is root, comma. So I'm raising here and going to be pk for the kth prime. This is rooted. And here I have gn. So, and now I'm ready to write the first theorem. Okay. There's a lot packed in this. We're going to unpack this in a second with a concrete example. But let's write the first theorem. So theorem GH, for the height is the forest that we seek. That means this is going to be the forest of all the trees that are correctly labeled and have height bounded by h. Okay? So while I was patiently waiting for you guys, I'll spend some time on an example. All right, so let's work through an example completely. All right, and to make it simple, we're just going to be looking at two labels. So we just have 2 primes, the 2 smallest prime. 1 is not considered a prime. 2 and 3 are the primes we're going to be using. All right? So we said G1 is simply going to be grafting this forest made of these 2 small branches and this one. And the resulting set is this guy. Okay? So you graft this guy to the root, you get the same thing. This guy to the root, you get the same thing. This is where these are coming from. You grab this one to this one, you get this. Okay? So now the recursion can start. Once I've defined G1, I want to recurse. So when G2 is this, G2 is defined as this forest grafted onto this one. Where this guy, remember I told you, I'm just raising a forest. So what forest am I raising? I'm raising exactly this one. So I wrote down here what it looks like. So if you look below 2, it's exactly what you have here. But if you look above, if you look above 2, you have exactly you have here, what you had here, but the root is being substituted by this branch. Okay, so you have 2 now here below, and here you have 3s. So the result of the grafting is never going to occur. You'll never have a situation where 2 siblings will be brothers. So let's illustrate. If you have a family here, you have the Bobs on this side and the Jerrys on this side. If you put them together in a family in some adoption scheme, you will never have a Bob and a Bob because they're coming from different names. So the claim is, what's going to happen here, because I'm performing a product over different labels, I'm never going to have an invalid tree. Okay, so that was lemma 1, and don't have invalid trees by construction. Lemma 2. So lemma 2 says that no 2 trees in the forest are the same. All the trees inside this forest are going to be different. This is also, I'll show by construction. So the trees in G1 are different except for the roots. So in this family, in the family of Bobs, I have the roots. And I have the Bobs. Here I have the Jerrys. And when I compute the product, I never get in a situation where the same tree appears because the entries were different. Okay? In here, same principle applies. Every time you compute the razor, you get different trees, and the grafting never grafts 2 things that are similar. Here's another way, a better way of saying it. How could you get 2 trees? How could you get the same tree twice? To get the same tree twice, you would have to have a product where this occurs. T1 is being grafted onto T2, and somehow you also have T2 being grafted onto T1. And the claim is this doesn't occur because the families are different as you're going from the side, so you never have flips. All right? Okay, so this is technical, but it's important. The final lemma is the following. So this is that Gn is always included, but so Gn plus 1 is bigger than Gn. In other words, you repeat, Gn plus 1 always includes everything that was in Gn. And these sets never have the same size. The reason why this happens is simply because of this root tree line there. He's going to hit this guy and repeat something that was in the previous sequence that is a tree that is smaller. Okay? So it took time to actually get familiar with this. I'm not assuming this is going to be trivial, but once we start manipulating these things, there are some great benefits. So how do we prove that actually we get all trees of height h? Okay. So the way we prove that we get all trees of height h is by contradiction. So there are 2 approaches to proving this. One that I like, one that I would like better, but I'm having trouble with. So contradiction goes as follows. Assume assume there is a valid tree T that we miss. So this tree has height bounded by h and tree that we miss. Okay. So this tree has height bounded by h and is validly colored. So the only way we can miss such a tree would be if we miss either the whole tree or we miss a subtree of that tree. Okay? So let's go through the recurrence of missing subtrees. So suppose this T here was here, and we're missing this branch somehow. If you miss this branch, then there must be a smaller branch that you're missing, and you can recurse all the way up to the level G1, where we guarantee that everything of height 1 is there. Okay, so you cannot miss something of height 1. And you use that recursively to say you cannot miss something of height 2, and you cannot miss something of height 3. So essentially, we unfold the tree to see exactly where it was coming from in here. So that's the idea for the proof by contradiction. The proof that I would like much better is the following. If you look at these trees, the resulting trees here of the grafting, these are all rooted subtrees of this one, the regular one. So what we're really looking for are rooted subtrees of a complete Edinah tree. So you have a complete tree where everybody has the maximum number of siblings. So you have a tree where everybody has the maximum number of siblings, which is necessarily n. And you want to find how many distinct rooted trees there are. So to prove that the algorithm works, it suffices to know how to count these guys and then claim that the algorithm produces exactly the same number of distinct rooted trees. Now, I do not yet know how to count these guys independently. This scheme allows me to count the trees that I'm generating here, but I don't know of an independent way to actually count rooted subtrees. So if anybody knows how to use generating function to prove this, I'll be definitely interested. Okay, so this completes the first part of the talk, which was the combinatorics. What in the world does this have to do with numbers? So this is a rhetorical question.
So far, you can do the primes.
Yes, so far.
But they really use prime probably for the second part.
Yes, so I was building the intuition for the second part. Why in the world are we using primes, and what does it have to do with numbers? Well, these trees, we want to think of them as not just counting rooted subtrees, but actually structurally encoding integers. And here's the scheme. Sibling relationship between vertices. Sibling relationship should equate into integer product. Integer product. That's first. Find any parenthood relationship. Should equate into integer exponentiation. So this is exponent. So integer exponent. Okay? So what does that buy you? Let's actually look at a concrete example and see that all these trees indeed are integers. And they uniquely encode an integer, so we are using the so-called fundamental theorem of arithmetic recursively. So everybody familiar with raising trees? Okay. So I'm going to consider an example. So consider the following tree, and we're going to see which number it encodes. So 5, 2, 3, 2, 14, 5, 7, 2. So the evaluation is performed starting from the leaves. So this is important to say because exponentiation of integers is not associative. Where you put the parentheses matter. Okay, so we start at the leaves. These are siblings. So this is a product. So that means what we're looking at here is 5 times 3. Okay? This is a parent. That means what we're looking at is an exponent. So this is to the power 2. All right? First parenthesis. First thing we evaluate. Okay? Now, this is a parent. So that means we're looking at 2 to the power, the whole thing. Now, these guys are siblings. Right? I collapse all of this to a vertex, so to speak. See, these are siblings. So I have to multiply this by 5. This is a sibling of 7. Right? By the way, 7 was power to the... There was a 2 power 7. So this is 7. The claim is, this is how you encode an integer as a tree, and this is bijection. And every time I give you a tree, you can give me an integer, and every time you give me an integer, I can give you a tree. So here's a proof that every integer encodes uniquely a tree through the bijection. So we know by the fundamental theorem of arithmetics that every integer I can be uniquely expressed as a product of distinct prime factors. And this is the reason why siblings must be different. You want to have distinct prime factors, so you don't allow siblings to be the same. They must be different. Well, the powers are integers. So you can, again, factor these guys. So you have a